Let's go ahead and look at electrophilic additions to conjugated systems. Previously, we've seen where if we undergo an electrophilic addition to a double bond, it typically follows Markovnikov's rules and adds the hydrogen to the least substituted carbon and the X to the most substituted carbon. Well, the same thing happens here with electrophilic additions to conjugated double bonds. If we're only going to add one equivalent of HBr, we'll yield one product. The problem that we're going to have here is that even though we follow Markovnikov's rules, we're going to get the possibility of two different products. We can either have a 1,2 addition or a 1,4 addition. And our conditions are going to matter depending on what product we want or we expect to get. So with addition reactions to double bonds, we can either get 1,2 addition or 1,4 addition. 1,2 addition occurs at low temperature. It's under what we call kinetic control. And that has, once you form the first step of the electrophilic addition of taking the hydrogen and putting it on the least substituted carbon, and then the internal carbon having the carbocation, the anion for Br minus comes in and attacks that carbon, and that's how you get the 1,2 product. But if we have the 1,4 product, that's going to be under what we call thermodynamic control, and that's going to be at a higher temperature. And what happens here is after you make the carbocation, the double bond rearranges. So the double bond migrates because it's an allylic carbocation, and now you get the carbocation on the terminal carbon, which then allows us to have a 1,4 product. So when a mixture containing predominantly the product 1,2, predominantly the 1,2 product is heated, the 1,4 addition product becomes the major product at equilibrium. So if you take and you run a reaction cold and you get the 1,2 product, you can convert it to the 1,4 product by adding heat to that system. Therefore, the 1,2 product is known as the kinetic product, and the 1,4 product is known as the thermodynamic product. So which one's better? Well, it turns out that there is greater stability of the 1,4 products. And that's because it has two alkyl groups bonded to the carbon-carbon double bond. So again, if you have the 1,2 product, such as 3-bromo-1-butene, that has less substitution on the carbon-carbon double bond, so it's going to be less stable. Whereas the 1-bromo-2-butene, the 1,4 product, is going to be more stable because the double bond has more substitution. The biggest reason why we get the 1,2 product is because of proximity. At low temperatures, you don't have a lot of heat in the system, so therefore your system is going to be going with the product that's closest to the intermediate. And since we don't have enough heat to undergo the rearrangement, we're going to have this proximity effect occur for the 1,2 additions. Now, as you'll note in the rest of your notes, there are a whole bunch of reactions dealing with Diels-Alder reactions. And I want to focus on these in class on Thursday so that you can see more information there. One of the things I will focus on now in the next video is looking at some of the other effects of ultraviolet light absorption on our conjugated systems.